So let's say we have this function over here, and this is the x-axis and this is the y-axis. How would we find the length of this entire function from this point to this point? Usually, if we just have a straight line like this, we could use the distance formula, which says x2 minus x1 squared plus y2 minus y1 squared, and the square root of that entire thing will give us the distance from this point to this point if this point to this point is completely straight. But here, we see that the entire function is curved. So we can't necessarily use this straight away. But what we can do is split the entire function into infinitely small little line segments. So this one is kind of big, but since this is a line, we can use the distance formula. So if we split this little line, or this entire function, into infinitely small lines, then we can use the distance formula. And let's see how to derive this. So first, we know that x2 minus x1 is just the change in x, so we can say that's dx. And the change in y, which is y2 minus y1, is just dy. Now we can say this is square root of dx squared plus dy squared. And now we're going to multiply by dx over dx because eventually we're going to have to create a definite integral which will evaluate the sum of the length of all the infinitely small little line segments. So after multiplying by dx over dx, because this is just multiplied by 1, we can move the denominator into the square root so it becomes dx squared. And then the dx squared over dx squared is just going to be 1. And we can simplify this to just say dy over dx whole squared. And we're left with this. And this is a formula to find if you're calculating with respect to dx. So if you have bounds with x, so like let's say this is x equals like 1 and x equals like 4, then you would use this. But if you are given the function in a form x equals f of y, where the function's in terms of y, then you would use this one, because then the question would ask you to find the length from, let's just say this is y equals 1 and y equals 4 again. So these are the two formulas that you would use to find the arc length, which is the integral from a through b, square root 1 plus dy over dx squared dx. And then the other version is c to d, square root 1 plus dx over dy squared and dy. Question 1, we have find the length of the curve y equals 3 over 2, x to the 2 over 3 from x equals 1 to x equals 8. So we're going to have to use the formula L equals a through b square root 1 plus dy over dx squared dx. And we're going to use this one because they gave the function with y equals, which is y equals f of x. So we're going to use this one. So first we need to find the derivative of the function. And this is just really simple, just using the power rule. We can just say dy over dx is equal to 3 over 2 times 2 over 3 is just 1. And then x to the 2 over 3 minus 1 is negative 1 over 3. So we have our derivative. And now if we just plug it in over here, L equals, and now the bounds of integration is going to be from 1 through 8 because that's what they gave us. 1 through 8 square root 1 plus parentheses x to the negative 1 over 3 square dx. And if you plug this into your calculator, you will get 8.35. And that's the final answer. Number 2, we have find the length of the curve x equals 2 over 3 of y minus 1 to the power 3 over 2 from y equals 1 to y equals 9. So this time, we're going to have to use the length is equal to the integral of c to d 1 plus dx over dy squared with dy. And we're going to use this because this time they gave the function in with the form x equals f of y, because here we have x equals, so we're going to use dy, and also they gave us the height instead of x equals something to something, they gave us y equals something to something. So again, we just have to find the derivative of the function. So dx over dy is equal to, if we just use a chain rule, 2 over 3 multiplied by 3 over 2 is just 1. So y minus 1 multiplied by 3 over 2 minus 1 is just 1 over 2. So this is just equal to the square root of y minus 1. Now all we have to do is just plug it into the formula. So L equals the integral from 1 to 9, square root 1 plus square root y minus 1 squared dy. And if you plug this into your calculator, you should get 17.3. And that's the final answer. Number 3, we have find the length of the curve x equals square root 36 minus y squared from y equals 0 to y equals 3. So again, we're going to have to use the formula L equals from the definite integral from c through d, 1 plus dx over dy squared dy. So let's find the derivative of the function. So here again, we're gonna have to use chain rule. So x equals square root a, and a is equal to 36 minus y squared. X prime is equal to 1 over 2 square root a, and a prime is equal to negative 2y. So let's substitute the functions. So we have dx over dy is equal to 1 over 2 square root, and a is 36 minus y squared, and this is multiplied by a prime, so negative 2y. So the 2 and 2 gets cut off, so the derivative is negative y divided by the square root of 36 minus y squared. So now let's plug it into the integral. So integral from 0 to 3, so 0 to 3, square root 1 plus negative y over 36 minus y squared dy is equal to, if you plug this into a calculator, you will get 3.14. The actual answer is just pi, but since we're only using 3 sig figs, we're just going to say it's 3.14. Number 4, we have find the length of the curve y equals e to the negative x from x equals 0 to x equals 2. So now we're going to have to use the length is equal to, from a through b, the definite integral from a through b, 1 plus dy over dx squared dx. So now let's find the derivative of the function. So dy over dx is equal to, since this is just e to the x, the derivative of e to the x is just e to the x. But since we have a negative in the exponent, we're going to have to bring it down. So negative e to the negative x is our derivative. So now we can just easily plug this in. So L equals from 0 to 2, 1 plus negative e to the negative x squared dx is equal to 2.22 if you plug it into the calculator. And this is our final answer.